let us discuss the LRU policy. So LRU says list recently used, right? So the policy says replace the block which is not used for the longest amount of time, right? Suppose you have many options based on its previous statistics which is not being used for longest amount of time, you are supposed to replace that, right? So here if you remember the victim selection, which one? The LRU block. So all the blocks essentially will be relatively positioned. We'll see. And कहाँ पे block आएगा? Where the new block will come? It will come to the MRU end, right? And block promotion क्या होगा अगर already है? Will there be any change? Suppose, yeah. So there is a cache, right? So one end will be our MRU end, one end will be known as our LRU end. Things will always go from this place. Things will always come to this place, right? And in between there will be changes. What changes? Let's say if you are having, let's say, A, B, C, D. Now if again reference for C comes, let's say C is already present, then what will happen? These things, this C will come to the MRU end, right? And then A, B, D. So this comes under block promotion. Block promotion, right? So that's what block promotion means. Right? Okay. So that's it. So in block promotion says it will move to the MR event in case of a re-reference, a hit. If you we are taking the same example, you can have a look and you can try to figure it out, So here we are assuming that this end is MRU end, this end is LRU end of the cache block. Again 4 places, that means 4-way set associative. Or it is a cache if it is a fully associative cache, so that means it has 4 blocks, right? Okay. Now initially cache is empty, so this happens to be same A1, A2, so A1 comes, now A2 comes, fine, again A2 comes, so A2 is this time it's a hit, and yeah, it is already there in MR event, so no issue. Now again A1 comes, so when A1 referenced, right, comes means it will come only once. This is coming. Now this means A1 is referenced, so A1 is already present in the cache. But the question is, they are present in this way. यहाँ पे A1 है, यहाँ पे A2 है. But this happens to be the MR event, right? This MR event. Now, whenever A1 is referenced, what will happen? A1 will come to the MR event. That's what block promotion is, BP. Right? Okay. Rest of the things are almost same. B1 comes, of course. B1 will be placed in the MR event. B2 is placed here. Now B3 comes. When B3 comes, you have to replace something. Which one will be replaced? Of course, A2 will be replaced because A2 is there in the LRU end. LRU block is replaced. Matlab, A2 is not out of all these blocks. A1, A2, B1, B2. A2 is not used for longest amount of time, right? That's what it says. When you are here, when you are standing here, so out of this you can see these 4 will be there. A2 is not used for longest amount of time. So that means, yeah, so it will be replaced. So then you will have this will be the content of the cache. Alright, so similarly at this place A1 will come, B4 will come, then A1 is referenced, but A1 is not present in the cache, it happens to be a miss. So you can see few misses I have written in red and few misses in black. We'll see in the next class, or maybe next to next class, the difference between this M and this M. Right? So just have these things in your mind. We'll see different types of M's or misses. Alright, so in that way we are done, and we can see that for this reference string which we have taken a simple one, and number of hits and misses happens to be the same, 3 hits and 9 misses. Right? This is to be reported. What is the number of hits and number of misses for a replacement policy? Right? So that's what is LRU. Now what I would suggest you to implement that. You can implement, of course not in hardware, but in software you can write some program. If nowadays some of you must be feeling very bored, or staying at home, what you can do, you can try to write some code for implementation of LRU. Right? What you can do, you can do it if you have already learned doubly linked list or linked list in your data structure course. You can do it with linked list. Otherwise you can also try to do it using array. Right? You give it a try to implement LRU replacement policy. All right. Okay. Now moving ahead, LRU predicts a near immediate rereference for a block, both on hit and miss. Why it is so? See, we have used a term called near immediate. So why it is so? Let's say so let's say what we have is essentially a cache, right? 4-way set associative cache. That means 4 option hai. So first A, B, C, D. Let's say the cache is full, right? Then the item will keep on coming. The request for the next one will come, right? Now let's say the items are next G, H, I, J, and let's say what else? Or let's say F, G, H, I, J, and some other F. Now what we'll do, so these are coming in this way, right, one after another. Now here F is referenced, and the F is referenced once more here. Now when F is referenced, what we'll do, if this happens to be your MRU end, right, once F comes, your cache becomes something like this. F comes here, right, your A, B, and C, because D will go. Now the policy is keeping F here, expecting that F will come in near future. If F is referenced in newer feature, then only the policy will take benefit of that, right? So in this case, F is not coming in near future. F is coming here, right? So whenever F comes here, the policy cannot take benefit of that. So यहाँ पे जब आएगा, by that time your cache will be filled up, because you have 4 places. Your cache will be filled up with G, H, I, and J, right? Eventually your cache will contain something like this, right? So the recent one, J, I, H, G, right? Something like this. So that means in this case we'll say F is referenced at a distant, right? So for this kind of things, LRU cannot perform well, right? Whatever material I'll share, if you're interested, you can go through that. You'll see this kind of things over there, and that paper will tell a propose one replacement policy. Of course, that we'll not discuss here, but to address this kind of problem of LRU. So this is just to give you an essence what happens and what are the things that we need to consider while thinking or designing or coming up with a replacement policy, right? Even if people are coming up, papers are coming up with newer and newer replacement policies with different kinds of applications, right? As I told, these patterns depends on the type of application we execute, right? So if F would have been somewhere here, then you could have we could have get benefit from that. Anyway, so that's what is a discussion on LRU. Now another characteristics of LRU is it's difficult to implementation is a bit costly in hardware, because you need to keep track of all the blocks, relative positions of the blocks. Now if you have k blocks, right, so you would need to have 2 to the power k bits, right? So that is one of the thing, and as a result many variations are coming up for LRU, and they are called pseudo LRU, right? So you can see a lot of variations of LRU. If you just go through the Wikipedia page, you will see that, right? Or other better implementation of LRU, right? Okay, so now we'll discuss one policy where instead of keeping 2 to the power k bit, we'll keep only 1 bit per block, right? 1 bit, of course, 1 bit per block. So what is the policy? The name of the policy is NRU, not recently used, right? And interestingly, this is used in many modern processors, right? Okay, now each block has an extra bit. This bit, the value of that bit will tell the characteristics of that block. If the value is 0, so that means the block is accessed recently and it is predicted to be accessed or referenced in near future, right? Similar to LRU, but we are keeping only 1 bit. If it is 0, it is predicted to be, it is a good block, right? To put it very simply. Now 1 says it is a bad block. The block is not accessed recently and it is predicted to be re-referenced in distant future. So you can replace that block, right? So essentially it tells these two things. Now what happens in case of a hit? In case of a hit, so hit means if you if you recall, so things are there in the cache, a request comes and it is already present. Request for, let's say, A comes and A happens to be already there in the cache. So then it's a hit. When a hit happens, the NRU bit of that block will be set to 0. Whatever is the NRU bit of A, irrespective of that, whenever a hit happens, it will be 0. Right? And in case of a miss, the first block with NRU bit 1 is selected for replacement, because whenever miss happens, then what happens, we assume that a cache is filled with some items and some, let's say, some E is referenced. Now of course E is referenced, that's why it's a miss. यहाँ से अगर कुछ रेफरेंस होता A, B, C, D से, तो वो हिट होता. अगर यहाँ से नहीं है, तो that means then only it will be a miss. Whenever it's a miss, so that something has to go from there, because the miss will be, it's a miss, then the things will be brought from main memory or the next level memory, right? And then it will be placed in the cache, If you recall your first class, so it will be placed in the cache. Now if it is to be placed in the cache, something has to go. Now the question is, which one will go? So the blocks having bit 1, NRE bit 1 will go, right? If you have multiple blocks with NRE bit 1, well, you can choose any order. The first block with NRE bit 1 is selected for replacement, and the new block, which one will come, its NRE bit will set to 0, right? So just to give an example of that, of the policy. So initially, again, you will have cache block and its NRE bit is all are 1, right? And things keep on coming to the cache, A1, A2, A1. So A1 comes, its bit is set to 0. A2 comes, set to 0, right? A1 is referenced, so anyway, it doesn't matter. It can be there wherever it is, because it's not a relative position, doesn't matter here, right? So you don't need to do any changes. B1 comes, yeah, its bit set is set to 0. B2 comes, set to 0. B3 comes, you need to replace something. The replacement will happen out of this. Now out of these blocks, if it is 0, everything is changed to 1. So all bit will become 1, 1, 1, 1, right? And the first one, any order. So we are going in this way. So the first one happens to be your A1. A1 will be replaced, right? And B3 comes here. All right. So then B4, the same will happen for B4, but when B4 comes, we have 3 blocks with bit 1, NRE bit as 1, so you can replace any one. Of course, we'll replace, as we are going from this way, so you replace A2, A2 will go and B4 comes here. Now then A1 is not present, so again B1 will go, A1 comes here, A2 comes here, right? And A3, so A3 for again, when A3 comes, flip all the bits to 1, 1, 1, 1, then the first one, so B3 goes, A3 comes, and A1 is already present in the cache. Now A1 is present, but its bit is set to 1. When A1 comes, its bit is set to 0, right? So that's a policy. You can see for this reference string, it is, the result is same. Effectiveness of that, as far as hits and misses are concerned, these are same, but for this you need only 1 bit per block to implement, and in LRU you need 2 to the power k block, 2 to the power k bits per block to implement, right? Okay, now we have seen that. Now what do you want? What can be the best possible way? What can be the best option, right? Now the best option is, you should replace the block which will be, you see the here word will be, or rather will not be, which will not be used for longest amount of time, right? जो बहुत दूर तक यूज नहीं होगा जो ब्लॉक, उसको रिप्लेस करो, right? Now remember, you are standing here. How do you know the future? Is it possible to know? Because it requires future knowledge, right? So that's why it is mainly of theoretical interest. And if new algorithm comes, new replacement policy comes, so it is said like how close is the policy with respect to the optimal policy, right? So that's how it is being used, and the goal is, the perfect scenario is the optimal one, right? Now for these, there are various ways, as I was mentioning in some of the thing about application profiling, or to see the behavior of the application. If you can somehow get the behavior of the application, we maybe come up with some good replacement policies, right? Now what I suggest you can try this algorithm, this policy, for the previous reference string. And as I often say, I also told in the last class, but I don't know how many of you have responded in the course platform. Anyway, I never lose my hope, so I keeping my hope on. I'm still telling you, yeah, you can try this one and you can report the result, right, for the previous string. And what you can also do, you try all the policies with some different reference string, right? You assume something from your side and you see whether it changes with the performance of the policy changes with the reference string or not, so as to give you a feel about different type of applications or different reference strings, right? So with this we have come to the end of our discussion, today's lecture. So what we have seen is essentially the cache replacement policies. As cache stores limited data, limited item, its size is limited, so eventually once it will become full, right, depending on the processor's request. Now when it becomes full, we need to do something some way so as to prioritize these contents of these locations, so that whenever there's a question of replacing something, you can decide which one will go, right? So that's what basically cache replacement policy deals with. Of course, it also tells where to place the block, and if whether there will be a change in case of heat, so stuffs like that. Now we have seen first in first out replacement policy with example, LRU with example, NRU with example, and we have also talked about something called optimal. What will be the scenario in case of optimal replacement policy, right? As I already told that these replacement policies are not only used for caches, they are used for other places where there is a question of replacement, right? And one popular example is the memory pages. With that, we wrap up today's discussion. Thank you.